In this video, we're going to look at relative motion analysis using rotating axes. And you have to excuse me, have a cold right now. And if you're using Hibbler's book on dynamics, this is section 16.8. Hibbler has a great book on dynamics, section 16.8. Now, this analysis involves having like a rotating system and then other objects moving on that rotating system. And I'll just briefly show the equations here. Like for velocity, you have, like, say the velocity of B is going to be V equal to VA, velocity of A, plus the cross product of the angular velocity of the main body with RBA, plus the velocity of B with respect to A. And then the acceleration is given by this equation here at number 2 there, which is acceleration of A equals, excuse me, the acceleration of B is equal to acceleration of A plus omega dot cross RBA, and then this term and this term. Now, this looks like a long equation, but we'll find whenever we break this down, these are pretty easy to use. Just remember that omega is the angular velocity of the main body, and omega dot is the angular acceleration of the main body. And RBA is a position vector directed from B to A, and acceleration of B to A is given by this. Once again, these look complicated, but this allows us to have a very easy way to analyze very complicated mechanisms. Let's take a look at this problem here. Find the velocity and acceleration of caller B at the instant shown. Notice the mechanism rotates about point A, but A is fixed. So we have this mechanism here. It's rotating around this way. And then on the mechanism, there's a caller that's moving 5 feet per second and accelerating at 4 feet per second squared. But the whole mechanism itself is rotating at 3 radians per second and accelerating at 2 radians per second squared. Now, with the method we're using, what we do, we analyze the whole system and this caller with respect to the system separately. And we'll take a look at that next. Now, again, we're going to take a look at this problem. And now I renamed the axis. I've made this the x-axis and this the y-axis. That'll make our calculations quite a bit simpler. And then I usually organize these in this way. I'll set up the moving reference here and the motion of point B with respect to moving reference here. Again, the one good thing about this method is you can do these things separately. In other words, everything over here has to do with the main body that's rotating or translating. And all you have to do is figure out what is it doing. So like in this case here, this body here is rotating at 3 radians per second, and that's going to be the angular velocity. Remember, in this method, the angular velocity is omega, so it's going to be 3 radians per second. And remember that if this is in the XY plane, it's rotating about the Z axis. So therefore, this 3 radians per second is going to have a K with it, representing the Z axis. And also the acceleration is 2 radians per second, which again, also about the Z axis. So that's going to be 2K radians per second squared. Again, that's the angular acceleration. Again, that's of the whole body. We're not looking at the part that's moving on the body, which is this color. We're just looking at the whole body. Now, notice that point A is fixed. So this mechanism, the whole mechanism, is not translating on the x-axis or y-axis. It's just fixed. So the whole body has no velocity and it has no acceleration. So it's not translating in any way. So now once we do the main body, we look at the object on the main body. So like it's this collar. And again, we're going to analyze this collar as though the main body was fixed. And so in this case here, we don't care when we're looking at this, we don't care that this is rotating. We're just looking to say, okay, this is on the main body. What is this doing with respect to the main body? So here it's moving again along the x-axis, along the positive x-axis. Again, that's why I defined it the x-axis this way. It'll make it much easier to analyze. It's moving 5 feet per second. And again, along the x-axis, that would be I. And then also along the x-axis, it's accelerating 4 feet per second squared. It has to be 4I feet per second squared. Now notice when we did the acceleration, we did not take into account the fact that this whole thing is rotating, because normally, remember from the section you did before, you would have to add a normal acceleration here. But because it's the main body that's rotating and not something on the main body, we don't have to take that account. In other words, those are done separately. Now, we're going to see an example later where there's something rotating on the main body, in which case we will have to have a normal acceleration. But again, it's very simple to set those up. See, all we had to do is say what the whole thing was doing and what the part on the main body was doing. The last thing that we need to do is find out RBA. And again, remember, RBA is just what does it take to get from point A to point B? Remember, it's always reverse order. So to start at point A, to get to point B, you have to go 4 in the x direction. So that's just going to be 4I like that. So now all we're doing after this is just calculations, nothing more. This is the most important part, setting this up. Now everything is just substituting into our equation. Again, these are the equations that I showed you at the beginning of the video. I wrote them out here. I added some parentheses in some cases here and here just for clarity. But now we've found everything on the right. We found VA, omega, RBA, VBA. We found omega dot, uh, acceleration of A, RBA, etc. So we have everything. Now it's just a matter of substituting things in. And let's go ahead and do some of this. Let me do the cross product. What I think I'll just show one or two of the cross products and then skip ahead on the video so you don't have to sit there and watch it. Then if you want to check your answers, you can go ahead and do that. It's the case where you might want to check my answers because I don't have any way of checking this because I made up this problem. It's possible. It's always possible I may have made some mistakes here. So again, this is omega cross RBA, which is this up here. And that, remember, omega was 3K, which is 003. And RBA was 4I 400. And if we do the cross product, you can see the I term is going to be 0. Again, remember, you cover this, and do that determinant. And now we'll cover this and do this determinant. So that'll be 0. Remember, the J is a negative. Remember, the first one's positive, negative, and then it's 0 times 0 minus 4 times 3, which is that one there, plus K. Again, for K, that's 0 times 0 minus 0 times 4. That's also 0. So we're just going to end up with, that'll be negative 12 and negative 12. That looks like that's going to be 12J like this. And I'll write down all these others. And like I say, I'll do these off the video so you don't have to sit there and watch them. But you can check to be sure everything looks good to you, that what you have matches. So I finished the other cross products, omega dot cross RBA, omega cross RBA, and omega cross VBA. And again, one thing I didn't mention at the beginning, I'm calling counterclockwise positive for the rotations, which is normal. And so there's all the calculation. Again, if I made a mistake in these are kind of tedious. Put something in the comments. I think they're correct. And now let's substitute everything into our equation up here. So for the velocity equation, the velocity of A was 0. And omega cross RBA, we calculated over here to be 12J. And then VBA, we had from the beginning, that was 5I. And so if we put them in order, we're going to have 5I plus 12J. That's going to be the velocity of that collar. Now for the acceleration of the collar, again, we have this equation here, that long equation. Once again, the acceleration of A was 0. And omega dot cross RBA was 8J. That's this here. Then this double cross product here was minus 36I. Then over here we have 2 times this cross product, which was omega cross VBA, which is 15J. Finally, plus the acceleration of A with respect to B was from our first page for I. And so if we work this out, let's see, we're going to have 4I and a negative 36I. It looks like a negative 32I. And then 30J and 8J looks like 38J, like that. So again, we solved a very difficult problem using this method. And again, this method is very easy for handling difficult problems because we break it down into the main body and a body or object on the main body. Let's take a look at this problem. Find the velocity and acceleration of point B at the instant shown. So we have, again, the main mechanism is moving counterclockwise at 3 radians per second, accelerating at 2 radians per second squared. But then on that main mechanism, we have another rotating disk that's moving, that's yeah, moving at 7 radians per second and accelerating at 5 radians per second squared. So again, this is a case, unlike the last one where we will have to take into account the normal component of acceleration because here we have this smaller disk is rotating and it's on the larger mechanism. So let's take a look at this. So just like before, we're going to set up these two columns, one for the motion, the moving reference, and the other one for the motion of point B with respect to the moving reference. Now, in the last problem, we redefined the axis as like X and Y, along this axis here. But in this case, it probably doesn't help because the B is off the axis anyway. So even if we were to redefine the axis, it's probably not going to help us. So I would say we might as well keep the axes as they are, call uh, this X and Y, and maybe again also use the positive and negative the way you would do for X and Y. Again, you could change the positive and negative if you wanted to. You could make to the left positive, but I think it's easier just to keep them consistently X positive this way and negative this way, Y positive this way, and Y negative this way. And again, just fill out our two columns. Our main body is rotating at 3 radians per second. Once again, it's rotating about the z-axis. So that's going to be 3K. And once again, I'm calling counterclockwise positive. Again, remember this notation. This is the angular velocity of the main moving reference. Then the acceleration is here. Once again, it's accelerating about the z-axis. So that's going to be 2 radians per second squared. And so again, A is fixed. So that means A is not translating. So we can make this 0 and this 0. It's not translating or accelerating. Now, if we look at point B up here, point B, and you probably can't see it, but I've marked this as C. Now, I actually named these points to kind of match so we can use our normal B and A. Sometimes if you get a problem, it won't work out this nicely that you can always use B and A in this way. Um, but though if you wanted to, you could always rename them if you're given a different problem. But I've kind of actually wrote the problem so we could use B and A. And so let's take a look at this. Again, the velocity of B with respect to A. And so that's going to be, again, this velocity here and the acceleration here. Again, we know it's going that way because it's rotating this direction. So the velocity of B with respect to A, it's obviously going to be going in the x direction. So that's going to have the I component. And of course, the velocity is going to be 7 radians per second times the radius, which is 1 meter. And that's going the I direction. So that's going to be 7, uh, 7 meters per second. Again, in the I direction, like this. Then for the acceleration of this, again, in the I direction, it's going to be, I'll just put the numbers out. It'll be 5, the angular velocity, angular acceleration, times a 1 meter radius. And again, that's going to be in this direction here. So that's I. Now, we're going to also have a normal acceleration, which is going to be towards the center of C. You probably can't see my arrow very good, but it's going to go. Remember, the normal acceleration is always towards the center of the object about which it's rotating, about the point about which it's rotating. So that's going to be, and I'm going to leave the sign off for a second. Remember, that's always velocity divided by radius. Velocity squared divided by the radius. Again, usually that's rho or r. In our case, the radius is just 1. And now notice, though, that that acceleration is going to be towards the center here. It's going to be directly perpendicular to this velocity here. It's going to be towards the center. And so that's going to be in the negative y direction. So that's going to be negative 7 squared over 1. And that's going to be 5i minus 49j, like that. And so then the other thing we're going to need is RBA. And so we're going to have to do a little bit of geometry here. So RBA is going to be, there's a few ways we could do this. We could actually find this length here. Let me put this over here. So this is 35 degrees. This is A, and this is C here. And we know that this length is 4 meters. Of course, the adjacent side is going to be 4 cos 35. And when you put in your calculator, I got 3.28 meters. And then this side over here is going to be 4 sine 35 degrees. Which is 2.29 meters. And of course, if you look at the picture, B is 1 meter above C. So it's going to be up here, 1 meter. So now we can write our RBA, huh? So if we do our RBA, remember that's what it takes to go from A to B. So along the x-axis, we have to go in the negative 3.28. direction. And then in the y direction, we have to go 1 plus 2.29. In other words, to go from here to here, it's going to be 1 here plus 2.29. It's going to be a positive 3.29 J, like this. Again, before you start calculating, it's good to have your equations in front of you or have them in mind. So if we look at our equations, we're going to need these cross products. So let's actually write these down. Again, we need these cross products. So let's actually go ahead and set them up. We have the angular velocity of the moving reference, which is 3K. So I'm going to just go right here and put them in. Just be 0, 0, 3. And then RBA, which we found a minute ago, is right up here. Plus 328, 329. I didn't realize how close those were to each other. So negative 3.28 and 3.29. Usually they're not going to be that close. That's just quite a coincidence. Once again, I'll just do this first one. Again, if we cover up the column in the row of I, we get this determined 0 times 0 minus 3.29 times 3. And then cover up this one. Again, J is always negative, and then 0 times 0 minus negative 3.28 times 3. And then finally, if we go over here, we end up 0 times 3.29 minus 0 times negative 3.28. That's just all going to be 0. And when you put into your calculator, you get this. And again, I'll go ahead and do the others off screen and come back and show them to you so you can see what the calculations are, but I won't take time in the video to do that. And here are the rest of the calculations if you'd like to check them. Again, omega dot RBA, and then this cross product and this cross product. And we get this and this and this and this. And next, substitute into the equations. VB is going to be equal to VA, which again, that's 0, because the moving reference was not translating. And then plus this cross product here, which was negative 9.87, negative 9.84. And then VBA was the 7I. And so it looks like VB, if we put those together, will be what? Negative 2.87I minus 9.84J, like that. Then next, we're going to substitute into this equation here. Again, the acceleration of A was 0. The moving reference was not translating. Then we have this cross product here, which was this. This was the negative 6.58I minus 6.56J plus 0. Okay, I'll leave that off. So that was this. Then we have this double cross product here. And that was this right here. 29.52I minus 29.61J. And so that was this one. Next, we need this one here. It only has a J component. And finally, the acceleration of B with respect to A. That was back from our first page, wasn't it? That was this 5I minus 49J. And again, if we combine all the like components, for the i's, we have negative 6.58, 29.52, 2 times 21, excuse me, that's not an I, 5. So negative 6.58, 29.52, and 5. That all gives us 27.94I. Then for the J's, we have negative 6.56, negative 29.61, 2 times 21, and then minus 49. That all comes out to 43.17 for the J's. And so again, we got the velocity of B and the acceleration of B.